Objective 7 deals with the Bronsted-Lowry theory of conjugate pairs. Bronsted-Lowry identifies acids as proton donors. And protons are the same thing as hydrogen ions. Bronsted-Lowry defines a base to be a proton acceptor. In a conjugate pair, the acid always has one more hydrogen. So acids proton donors, bases accept the protons, and protons are hydrogen ions. Let's give a read through of Objective 7. We're to identify the conjugate base associated with the Bronsted-Lowry acid and give the acid if we're given the base. So hooking together the conjugate pairs. Example 1. Give the conjugate acid of the following bases. If we are looking at bases, we understand to turn it into an acid means to add one more hydrogen to the formula. Only one hydrogen at a time. And when you add a hydrogen ion, it becomes one more positive on the number line. Make it one more positive on the number line. So, beginning with water. Water originally is written as H2O. If we add a hydrogen ion to create an acid, the conjugate acid H3O, now going from neutral water up 1 unit on the number line to a +1 charge. The H3O plus hydronium ion is the conjugate acid of water. Letter B, dihydrogen phosphate ion. The dihydrogen phosphate ion has the original formula from our polyatomic chart as H2PO4, and it carries a -1 charge. Dihydrogen phosphate ion gains one more hydrogen to form the neutral molecule of phosphoric acid, H3PO4. Think on the number line. When the -1 moves up 1 unit on a number line, it is now neutral. Letter C is ammonia, NH3, the formula given to us. Add a proton, add a hydrogen ion, and we form ammonium, NH4 +1. Again, thinking on the number line, ammonia is neutral. Move up 1 positive position and you go to the +1 spot, NH4 +1, ammonium. The nitrate is a polyatomic ion that starts originally with NO3, -1, nitrate. Add on a hydrogen and we form the conjugate acid of nitric acid, HNO3. The ion was -1, the acid becomes neutral. Our second problem says to give the conjugate base of each of the following acids. So it's the opposite direction. When we remove a hydrogen ion, the acid turns into its conjugate base. Remember, make it go down 1 on the number line, a -1 when we remove a proton. So, if the original formula for hydrophosphoric, hydro root word ic, hydrophosphoric comes from the element phosphorus, H3P, hydrogen phosphide would have been its name, hydrophosphoric is its acid name. Remove just 1 proton and we get H2P, and moving 1 unit down on the number line, it now carries a -1 charge, H2P, -1. Letter B is water. Take a hydrogen off of the water and form its conjugate base. Its conjugate base is called hydroxide, OH, -1. Notice water was neutral. Slide 1 more negative spot on the number line and you find the -1 position. Ammonium is our polyatomic ion, NH4 with a +1 charge. When ammonium loses its proton, it goes back to its conjugate base, ammonia, NH3. Ammonium as a conjugate base of ammonia. And the last one in this series is carbonic acid. Ic came from 8, so we looked up the polyatomic ion called carbonate. Carbonate was a -2, so when I formed its acid, we placed 2 hydrogens. However, when you form its conjugate, only one hydrogen gets removed, HCO3, now carrying a -1 overall, is the bicarbonate or hydrogen carbonate ion. Carbonic acid started neutral and it went down the number line to 1 negative bicarbonate ion. In our third example, we're being just asked to label the conjugate pairs. We understand the pattern of the Bronsted-Lowry, that on the left side of our equation we must have one acid and one base, and on the opposite side of our equation we must have a conjugate acid and a conjugate base. I think it's easiest if we hook together those ingredients that are only different by one hydrogen ion. For instance, SO3 -2 has a conjugate on the right-hand side. HSO3 -1. These two are only different by one hydrogen in their formula and therefore are conjugate pairs. The one with more hydrogen is always labeled the acid, and on the right of our arrow are the conjugates. So HSO3- is the conjugate acid of the base sulfite. If sulfite is a base, water must be the acid because we need one of each on the equation side. And if water is acting as an acid, its conjugate base is hydroxide. The letter B, hooking together the conjugates. I notice that HI has a conjugate way at the end, I-. Those two are only different by one hydrogen ion in their formula. The one with one more hydrogen is always the acid. Therefore, the conjugate base is iodide. If HI is acting as an acid, water must be acting as a base. We need one of each on the left side, and it forms its conjugate acid, hydronium. And in the last example, I notice ammonia can be hooked to ammonium, its conjugate. Those two are only different by one hydrogen. The same is true for acetic acid and the polyatomic ion acetate. With ammonia and ammonium, the one with one more hydrogen is always the acid. The conjugates appear on the product side, making ammonia the base, and its conjugate is the ammonium ion. Acetic acid is labeled as the acid, and its conjugate base is the acetate ion. And there is our seventh objective.